Hello YouTube. Today we're going to be talking about drag and terminal velocity. In particular, the parts that are really going to matter are the terminal velocity parts. The drag parts are going to be, they'll exist, but like, I'll just qualify it when we get to it. So, ideally, you'll be able to use calculus to model the motion of an object with air resistance. The big parts of this are making the force equation for the object, like doing like the free body diagrams and stuff. Setting up your differential equation is going to be sort of the part that is less important. And the part that's probably most important is conceptually understanding why terminal velocity happens and then being able to build that if they give you a different equation for drag. Because oftentimes they'll either give you the equation for drag just as part of the test, or they'll give you a new one explicitly within the problem. And they don't have these equations on the equation sheet because you're not expected to know them. You are expected to know the concepts, though, for sure, and you're expected to be able to use any drag equation that they give you. Cool. So, air resistance is a thing that exists. Pretty much, when you have to push air out of the way, that air is going to push you back off of Newton's third law. And there are a lot of different drag equations that'll work for different scenarios. But generally speaking, you'll get more air resistance if you're going faster because you will push a greater volume of air out of the way. And anything that makes you push a greater volume of air out of the way will mean that there's more air pushing against you, so you'll get more force from that air. So that also means that if you have a larger cross-sectional area, meaning if the amount of, if I take this calculator, this has a larger cross-sectional area than this because if it's coming towards you, because this has to push a greater volume of air, like the rectangle that moving this like this makes has much more volume than the rectangle that moving this like this makes. And that has a greater volume than this, which is the sort of smallest configuration for this object. So literally it could be the same object, just oriented in a different way, and you'll get a different amount of drag. If you have a rougher surface, or if you have a surface that just catches the air in a different way, you'll get a higher drag coefficient. So you'll get more drag. It'll be like the coefficient of friction was, honestly, where it's just sort of a thing that's a property of the object that has no units. And lastly, the denser the air is, the more air resistance you'll wind up having because there's more air that you have to push out of the way. So when you take all these things together, first off, again, conceptually, you should know that all of these happen, right? Just if you're able to look at the situation and think, what would make there be more air that I'm pushing out of the way? That will also make there be more drag. This is the equation that winds up coming from that, which is that your drag force is going to be 1/2 times capital C, which is your drag coefficient, times rho, which is your air density, and that one should stay pretty constant. You're falling from insanely high up. Capital A is your cross-sectional area, and V squared would just be your velocity squared. And the problem is that this equation changes depending on how fast you're going. So previously, forces haven't depended on your speed. Now they do, which makes things a little harder. So for terminal velocity, the big thing is that because the faster you go, the air resistance gets bigger. And because the air resistance keeps getting bigger, but gravity doesn't, eventually they wind up being the same size as each other. And once they're the same size as each other, you stop going faster because your forces have become balanced. You don't stop moving, you stop going faster. And that speed at which you stop going faster is called terminal velocity, terminal meaning final. And so that's just sort of a thing that happens, is that most objects, if not all objects, will have a maximum speed at which they can fall naturally due to gravity, because it'll be the point at which they're falling so fast that their air resistance is the same as gravity. So generally speaking, if you can reduce air resistance, your terminal velocity will be much higher. If you can increase air resistance, your terminal velocity will be lower, because that you'll hit that point where you're balancing out with gravity sooner. What this winds up looking like on a graph is if you go faster, you get less acceleration. So if you were to graph velocity versus acceleration for an object, you would wind up with something somewhat like this, where it's a curve, where you get diminishing returns, and it will asymptotically... Sorry. If you look at a graph of your velocity versus time, that's the one that I was actually going for. You'll get something like this, where it's this curve where your acceleration decreases and decreases and decreases and decreases the closer you get to terminal velocity. And you'll sort of asymptotically approach that terminal velocity. So what is terminal velocity? Well, the final equation winds up being this, but since whenever we ever let that be good enough, I just wanted to make sure it was in the slides. So let's think about it and figure it out. So the big thing math-wise, and this is the huge sort of takeaway from today, is that if you've got your object and you've got drag going up and you've got gravity going down, then your normal equation for this will be that your force of drag minus your force of gravity will need to equal your mass times your acceleration. Sorry, I just realized something. So we'll need to equal your mass times your acceleration. Specifically at terminal velocity, though, the reason it's terminal velocity is because you stop speeding up. So the reason it's terminal velocity is because your acceleration has become 0. So specifically if you're solving for terminal velocity, we'll get a more general form of the equation later, which is not going to be my favorite. This acceleration will go away. And so again, only at terminal velocity, you'll get that your drag force minus gravity needs to equal 0. And what this means is that at terminal velocity, your drag and your gravity will balance with each other. So if we take this and we go ahead and we plug in our drag equation, and we pop that in over here, what we'll wind up with is that 1/2 times the drag coefficient times the air density times the cross-sectional area times our velocity squared will need to equal mg. And so if I want to get mg alone, all I have to do is divide by this, or sorry, if I want to get my velocity alone, because specifically this will be terminal velocity, I just have to divide by 1/2 capital C A rho, and I'll get the order right on the next line. which will give us this, and that'll be 2mg over c rho times our cross-sectional area. And we can square root that, and we'll get our terminal velocity equation. So this part of it hopefully wasn't too bad. It's mostly just algebra, but the big thing, again, is that you conceptually need to know that the reason it's terminal velocity is because that's when your force of air resistance is equal to your force of gravity, so they balance out. The problem is that if you want to get a more general equation for this, you're going to have to do some differential equations, because you can't just get a function for velocity in terms of time the way you normally would by just like taking a normal integral, because there kind of isn't just like a normal
Hi everybody.
Right. I do want to briefly swap something around when I do that derivation, but we'll get to that in a sec. Okay, so if you wind up, and don't memorize this, but do pay attention to the process, ask some questions about the process after you've had a chance to see the video. Because this is something that you will have to roughly be able to do, but you won't have to be able to do this part specifically, because there isn't like you don't have this in an integral table basically, and if you did have it in an integral table, it'd be fair game. If you don't have it in an integral table, it is not fair game. So hopefully that makes some level of sense. So this is what our final answer will wind up being. It involves a hyperbolic tangent function, which is just a function that exists in the world. And its properties are basically that it just makes that curve that asymptotically approaches terminal velocity. Actually proving it, though. So pretty much what we're going to do is go back a bit and go back to our free body diagram. Now I'm actually going to change something about my equation. I'm going to conceptualize down to be positive. So what that'll do is it'll mean that we'll have the negative force of drag plus mg, and that'll equal ma, because this way our acceleration won't wind up being negative. And it makes it so that some of the identities work out a little better than they would have otherwise. From here, we're going to go ahead and plug everything like we did before, but we can't plug in that our acceleration is 0. Next step here is basically to just sort of go ahead and say, all right, this is going to be awful. I don't want to rewrite this stuff every single time that I do anything. So I'm just going to go ahead and say that there's some constant k. And that constant is equal to 1/2 c rho a v squared. Oh, not v squared, sorry. Just the stuff in front of it. And so when I rewrite this, we'll just get negative k v squared plus mg equals ma. From there, the problem with trying to turn this in as a function of time is that we don't really, like, we can't just integrate both sides, because if we integrate acceleration, it'll give us velocity, or if we integrate velocity, it'll give us position. And so that'll give us our velocity as a function of both position and time, which we don't really want. What we can do, though, is take a look at acceleration and think about what else acceleration is equal to. In particular, it's equal to the derivative of velocity with respect to time. And the nice thing about this is that our only two variables now will be velocity and time, which are the things we actually want. So if I go ahead and either divide each side by dv and then flip it, or multiply each side by dt, and then, which you're sort of not supposed to do, but we're just going to do it. And multiply each side by dt and divide each side by this stuff, which I think is the one we're actually going to go with. What we'll wind up with is that dt is equal to m dv over negative k v squared plus mg. And just for the sake of basically just for the sake of not having to write m a bunch of times, I'm going to go ahead and distribute this down to the bottom by multiplying the bottom through by 1 over m. And so what we'll wind up with is that dt is equal to dv divided by negative k over m v squared plus g. And so now what we can do is take an integral over our bounds of integration. For time, we're going to be going from 0 until the time when we actually finish. For the velocity, we're going to be going from 0 until the velocity that we're actually looking for. So this is basically an indefinite integral, except we know that if the thing starts at a location of 0 or a velocity of 0, this is specifically in terms of if you drop it from 0. We'll be able to find our velocity as a function of time. If you're not dropping it, you would have to change your bounds of integration, and you would actually get a different equation. That would depend upon your initial velocity. This is the part that's annoying. If we want to find this integral, we basically just have to look it up in the table of integrals. The equation form that we wind up finding is going to be for one of variable plus the thing, or sorry, variable minus the thing squared, and we'll just pull out a negative to make that be true. When we do that, what we'll wind up with is that equation that I gave at the beginning. And you'll have to do some more algebra from there. Like it doesn't give you the hyperbolic tangent. It gives you the inverse hyperbolic tangent. I'm not actually going to show that part. There's a lot of really good videos that other people have done that show that part. And I think that the better look, I guess, or the better way to go about it is just to skip straight to that end. So the end of this integral is going to be that velocity as a function of time will equal the square root of gm over k times the hyperbolic tangent of the square root of gk over m times time. And where k is still that 1/2 drag coefficient times the air density times the area. Something that's a little bit interesting about this is that because this is actually just terminal velocity, as the hyperbolic tangent approaches infinity, you get 1. And so because as the hyperbolic tangent approaches infinity, you get 1, this function winds up just giving you this function just winds up giving you terminal velocity as time goes to infinity, which makes sense. Parts I actually care about you being able to do on your own. You should be able to set up an equation like this for a force, even if your force depends on your velocity or if your force depends on your position, you should hopefully be able to set something up that looks kind of like this. You should also be able to look at it and try to be like, okay, well, these are 2 different derivatives of position, so I'm not going to be able to take an easy integral. But what I can do is think of the acceleration as the derivative of velocity with respect to time. Once we've done this, we can go ahead and take this part and actually set up an integral. Isolate one variable that you need to integrate, time. Isolate the other variable that you need to integrate, velocity. So if you could get from here to here, you're in great shape. And then know that you just need to do an integral. That's the part that I care about you being able to do. Not going to be too many chances to practice it. I'll try to make sure that I find and assign. There's an old open response question so you can see what type of thing they would expect you to do and get some practice doing it. But this is what the part that I care about. Not afterwards, because I didn't even show it because it's kind of a nightmare and I don't want to waste either of our time. So that's that's pretty much it with drag. Again, the big takeaways are at terminal velocity, your force of gravity is going to be equal to your drag, and that you can set up an equation to find velocity as a function of time. You might have to do some weird stuff where you sort of think of your acceleration as the derivative of velocity with respect to time, specifically because your forces will be velocity dependent. And then from there, you can break it up and solve it out. And then once you get to the point where you can take an integral, your integral should just be in an integral table. And that's pretty much it. All right. Goodbye, YouTube.